Okay, hi guys. This is a video on the math side of chapter number 13. And one of the tasks that we're asked to do in this chapter is to determine the amount of energy that it takes to change the state of certain substances. And this is pretty related to something we've tackled in a previous chapter when we looked at specific heat capacity and how much heat energy it took to change the temperature of an object. In this case, we're going to say, hey, it also takes some energy to change the state of an object, and we want to determine how much energy that is. And then we're going to end up putting both of them together so that we can look at what would it take to, say, take a chunk of ice at some known temperature and turn it into steam. But let's not get ahead of ourselves. So first off, let's take a look at a simple phase transition problem. Okay, and a problem might look like this: how much energy does it take to melt 15 grams of ice? So in order to solve this problem, we need kind of two things. We need a formula, and then there's a known quantity that we're going to have to use that's been experimentally determined for water. And so let's tackle both of those things first. First off, our formula for this is going to be very easy. It's only two variables. Well, I guess three variables. Q is the amount of heat. So that's going to be our answer to this question: how much energy? The heat is the energy being transferred. It's going to have the mass of the object involved, because obviously if we wanted to melt a chunk of ice the size of Lake Michigan, it would take significantly more energy than, say, an ice cube in your drink. So the amount of energy depends on the mass. And it also depends, as we saw from Professor Dave, it also depends on the strength of these intermolecular forces. Every substance has a different strength of intermolecular force, and so we have to have a factor for the substance that we're dealing with that'll tell us how much energy it takes to melt a gram of this stuff. And that's awesome because these are experimentally determined, and so therefore they'll be typically provided for you in the problem. In this case, we're going to call that variable in our equation a delta H. And let me jot this down. This is mass. And what delta H is the enthalpy of this particular reaction. Now we're going to be melting, and if we remember back, melting in science, we're going to call fusion. And so we're going to call this delta H sub F, or the enthalpy of fusion. Now, that's a number that's just independent for different substances, and it's kind of similar to that C from our Q equals MC delta T formula, C being the specific heat capacity. That was different for every substance. Delta H is like that too. It's different for every substance, and it's different for whether we are melting that substance or whether we are vaporizing that substance. And again, those differences just come from the different strengths of molecular bonds. Now, all that being said, these delta H's will either be the part of the problem you're asked to solve for, or it would have to be provided for you. And so in this case, delta H of fusion for water is 334 joules per gram. And now we're essentially done with our problem. We just have to plug and chug, put the numbers into the formula, and shake it until an answer comes loose. So we're going to say here, we're looking for Q. That's how much energy it takes. We have a mass given to us for M of 15 grams. And we're told that delta H of fusion for water is 334 joules per gram. Grams, which will leave us in the end just with this unit of joules. And if we take 15 times 334, we'll see that there are 5,010 joules required. So that's how much energy would be required to melt this ice cube. Now, quite often in these problems, um, well, I guess before I jump to the next one, let me throw another one in here. And let's just say, let's take that same 15 grams, but now let's say it's water that's at 100 degrees. It's ready to vaporize. But how much energy for that 15 grams of water that's at I should have specified a temperature in that last one that it was at freezing at 0 degrees. And here at water at 100 degrees. So this water is already as hot as it's going to get as water. It's ready to vaporize. How much energy does it take to vaporize this water? Okay, so this is going to be the same sort of problem as we just did, except now instead of Q equals M delta H sub F, we'll say delta H sub V, the heat of vaporization. It's a different amount of energy to vaporize a substance than it is to melt it. So again, though, that delta H will typically be given to you, and for water, it's 2,260 joules per gram. So again, this is now the simple plug and chug, same thing as our last formula, where we would take and say, well, the amount of energy is going to be this 15 grams times that 2260. And we can see that it takes actually substantially more energy to vaporize water than it does to melt it. And so we have 33,900 joules. So, yeah, look, it takes about 6 to 7 times, actually about 7 times as much energy, just under, as much energy to vaporize a substance as it does, or water in particular, as it does to melt it. Okay. So that's simple phase transitions, that's melting, that's vaporizing. If we were condensing, we would do the exact same calculation, except that it would give off this 5,010 joules instead of absorbing it. If we were condensing water from steam to liquid, we would give off this 3,300 or 33,900 joules instead of absorbing it. So we could put the signs backwards on those, making a negative 5010 to indicate that the reaction is losing this energy. And we could list it as, again, the negative 33,900 if we were condensing, because that substance that would be exothermic could be giving off the energy, and therefore the delta H should be negative. Okay. Remember that enthalpies, delta H's, I know we briefly addressed this in the past. Enthalpy is just basically, long story short, it's basically the stored energy in the chemicals. And so if they're giving off energy, then their stored energy is going down, and delta H must be negative. Anyway, back to the mathy side. We can do these same sorts of problems, but with substances that aren't at 0 degrees or at 100 degrees or whatever their relevant boiling and melting points are at. And should be comfortable with doing those because we have already learned how to determine the energy it takes to change their temperature. So all we're going to do now, we're going to take that old knowledge, we'll change the temperature to the melting point, then we'll melt it. And so it's going to be combining this Q equals MC delta T problems that we've worked with in the past with this new Q equals M delta H problem that we're being introduced to now. And so, for example, this next problem, how much energy to melt 15 grams of ice that is at negative 20 degrees Celsius. This is going to take 2 steps because we can only melt ice at 0 degrees Celsius. So the first step is get the temp to 0. And then once our temperature is 0, then we can melt it. Okay, so our first thing, get the temp to 0. Now this is a temperature change problem. We've done these in the past. Our formula, to refresh our memories, is Q equals MC delta T, where Q is the heat, M is the mass, C is that specific heat capacity that's different for every substance and will typically be given to you. And delta T is the change in temperature. Okay, so we've got all these things for this problem. It's just, well, not listed for you, but C for water is 4.184. C for ice is 2.06. And I should write ice and water. And C for steam is 1.87. And so we're actually not going to need all of those on this problem, but those, again, that would typically be provided for you. So in this particular problem, we're getting the temperature to 0. We're looking for how much energy that takes. So we're looking for Q. We have a mass given to us. There's 15 grams of this stuff. C is the specific heat capacity. Now we're below 0, so we have ice. So we need the specific heat capacity of ice, which is that 2.06. And then we need our change in temperature. Well, we melt at 0, we boil at 100. And so we need to get this temperature up to 0 so that we can melt. So we're always looking to change our temperatures to get to 0 or get to 100 so that we can do our phase transition. In this case, we want to get to 0. The temperature was at -20. And so if we go, we want it to end up at 0. So if we go 0 minus -20, the way we find a change, any delta, final minus initial, that'll tell us that our answer there is 20. We're changing our temperature by 20 degrees Celsius. Now we just run these things through the calculator. And we would find out in this case it would take 618 joules to raise the temperature of this ice. Okay, now we have a chunk of ice that's sitting at 0 degrees Celsius, and now we want to melt that ice. So now we're going to do the same thing we just did a couple of problems ago. We're going to take a chunk of ice at 15 grams and we're going to melt it. And rather than replicate that work, I guess I will. We just did this above, but we said Q equals M delta H, and that's delta H sub F for fusion, for melting. And so this was that 15 grams times the 334, that's delta H sub F for ice. And if we multiply those things, we got that 5,010 joules. So now if we look at this problem, we had to do two things, and each one of them cost us a little bit of energy. First, we had to raise the temperature, and then we had to change the state. And so if we want to find out the total amount of energy required to do this, we simply need to add those two things. We put in 5,010 joules to melt it, and we put in 618 joules to get that ice ready to melt. And so that would end up being 5628 joules. And there's our answer. That's the amount of heat. Okay. Now, the same problem can be expanded, right? And we could go even bigger. What if we don't just want to melt this ice? What if we also wanted to turn it into steam? And so it's going to be a couple of more steps, but it's not any more complicated because each one of these steps is either going to be a change of temperature, which is a Q equals MC delta T problem, or it's going to be a change in state, which is a Q equals M delta H problem. And so we just got to kind of keep track of what we're doing and then apply the appropriate formula for each step and then add all those results up at the end, and we can do, well, up to a 5-step problem. So let's see an example of one of those. And I'm actually going to modify what I wrote here. So we want to take it not at 100 degrees C, but let's say 215 degrees C. Okay. Now I've got some ice and I want to turn it into steam. And so I've got to do a couple of things. I've got to take its temperature. I've got to get its temperature from that -35 all the way up to 215. And I also, though, in the middle of changing that temperature, have to melt this ice because you can't have ice at 215 degrees Celsius. Well, not under normal atmospheric conditions. And you then have to take that liquid water that you've made and you have to boil it into steam so that we can get it above 100 degrees Celsius, as that's as hot as water will get in normal atmospheric conditions. So, what do we need to do? Well, first, we need to raise the temperature of this ice from negative 35 degrees Celsius to 0 degrees Celsius so that we can melt it. Then we need to melt it. And then we need to take that. Now we'll have a puddle of water at 0 degrees Celsius. Now we need to take that liquid water from 0 degrees Celsius to 100 degrees Celsius. After we get it up to 100 degrees Celsius, we can vaporize it. And after we have vaporized it, we can take that steam from 100 degrees Celsius up to the 215 degrees Celsius. So one of these problems, this is like as hard as this class of problem gets. One of these problems can be up to 5 steps, depending on what phase transitions you need to go through and how much the temperature is changing. Good thing is all of these are pretty simple steps. And so as long as we can get this part down, and that we remember that changes in temperature are Q equals mc delta T, and changes in state are Q equals m delta H, then the rest of the problem kind of falls into place for us. So let's get chopping at this and see just how easy this is. I know it can look intimidating, it can seem hard the first time you're doing it just because there are multiple steps, but it really is not a difficult problem. Okay, so let's just, as long as we keep it in these small chunks. So let's just start going. Okay, Q equals mc delta T, changing temperature. Okay, I want to find out what Q is. I've got a mass and, oops, I didn't have a mass, but we'll keep working. Let's go with 25 grams. Okay, so we'll go with 25 grams of ice. Okay, and if we're going to take that from negative 35 to 0, we need the mass, we need the specific heat, which again for ice, we have ice. So we're going to use C for ice, 2.06. And we're going to change its temperatures by 35 degrees Celsius. That will run all these through a calculator at the end. That chunk is now done. It's just that easy. Melting is Q equals m delta H. So Q equals our 25 mass. And the delta H, in this case, it's delta H sub F, is 334. And we're done with that step. Now we have to change the temperature from 0 to 100. So that's a Q equals mc delta T problem. Again, we have our 25 gram mass. C now for water is 4.184. And we're changing the temperature by 100 degrees. That step's done. We're vaporizing. Vaporizing is a change in state. Q equals m delta H. So our Q equals 25. And our delta H for vaporization is 2260. That step's done. And finally, we have a change in temperature. Change in temperatures are Q equals mc delta T problems. And we're going to put in our mass, 25 grams. We're going to put in our C for 1.87. And then we're going to put in our delta T of 115. And that step's done. Now, the only thing I've got left to do is just literally run all these things through my calculator and then add up all of the results. Now, the best way to do this is just leave everything right in your calculator. It will handle it. You can just literally type everything in you can see in order, and the calculator will handle it for you. That prevents you from any midstream rounding or truncation errors. So we're going to go and I'll literally show you that you can do this just all in a row. So 25 times 2.06 times 35 plus 25 times 334 plus 25 times 4.184 times 100 plus 25 times 2260 plus 25 times 1.87 times 115 equals. And there's our answer. Well, I guess it doesn't show up very well on the document camera, but the answer is 82,000. 488.75 joules. Again, if we were actually going to sig fig this thing, that would turn into 82,000 joules. And that would be our answer. So that's as big as these problems get. Hopefully that wasn't too bad. Remember, only 2 formulas, one of which we've worked with before. So really only one new thing here, and then a bit of a new application. If you have any questions, hit me up in office hours, by email, or by appointment.